Hi there, this is the review for simplifying radicals, and as always, I am the amazing Mr. Jansen. So let's go ahead and take a look at this guy. Taking a look at these first couple, when we're doing the square root, in order to take the square root of something, it's got to be a perfect square. So I want to break these into perfect squares and then take the square root of each perfect square. So for example, 48 can be expressed as 16 times 3. And 16 is a perfect square. Now, there are other perfect squares that divide evenly into 48, but 16 is the largest perfect square, and we always want to try to find the largest perfect square. The square root of 16 is a 4. It goes to the outside. He's a changed number on the outside, but his buddy 3 still trapped underneath the radical. So I take the square root of each perfect square and write that on the outside. Whatever's left stays underneath the radical. Same thing with number 27. The perfect square that divides evenly into there is a 9, so it's 9 times 3. And then the square root of 9 is a 3. I put the 3 on the outside. It's a changed number on the outside, but there's still a 3 that's trapped underneath the radical symbol. For 168, again, there are more than one perfect square here, but the largest is 81, so it's 81 times 2. The square root of 81 is a 9. It escapes the outside as a changed number on the outside, but the 2 is still trapped. And that's it. For number 4, it's a perfect cube that we're looking for this time because it's a cube root. So perfect cubes, the largest perfect cube that divides evenly into 32 is going to be an 8. So it's 8 times 4. And then the cube root of 8 is a 2. So again, I write it on the outside as a changed number on the outside. The 4 is still trapped this time. So with square roots, we're looking for perfect squares. Cube roots, we're looking for perfect cubes. For this one, I do the same thing with the numbers. So when I approach this, the 50, I can rewrite as a 25 times 2. And then for variables, it just needs to have an exponent that's divisible by 2, okay? An exponent that's divisible by the root. So for this one, I'm going to rewrite it as x to the 4th times x. And then y to the 10th times y. And then the z, I can't write as a perfect square because it's just a z. So now I take the square root of each perfect square. Square root of 25 is a 5, goes to the outside. It's a changed number on the outside. The square root of x to the 4th is an x squared. It's a changed variable on the outside. The square root of y to the 10th is y to the 5th. And that's it. That's all I can take the square root of. So I'm left with the 2, the x, the y, and the z underneath. And that's all there is to it. For number 6, the square root of 72, I can break down into 36 times 2. X to the 7th, I can break into x to the 6th times x. And then y to the 10th is already a perfect square. Z to the 3rd is z squared times z. So again, I take the square root of each perfect square. The square root of 36 is a 6. The square root of x to the 6th is an x to the 3rd. The square root of y to the 10th is a y to the 5th. The square root of z to the 2nd is just a z. And now underneath my square root, I still have a 2, an x, and a z. And that's it. For the next one, again, looking for perfect squares here. So I've got the square root of 24 is 4 times 6. X to the 5th, I can break into x to the 4th times x. And then y to the 8th is already a perfect square. I take the square root of 4 as a 2. The square root of x to the 4th is an x squared. The square root of y to the 8th is a y to the 4th. And now underneath my radical, I still have the 6 and the x. For the next one, there are multiple perfect squares that divide evenly into 128, the largest of which is a 64, so it's 64 times 2. X to the 9th is x to the 8th times x. And now I start taking the square root. Square root of 64 is an 8. The square root of x to the 8th is x to the 4th. And now underneath the radical, I still have a 2 and an x. For number 9, again, I break it into the perfect squares. This is going to be a 36 times 2. I can't do anything with just the x, so I'm going to leave it the way it is. And then y to the 6th is already a perfect square. Square root of 36 is a 6. The square root of y to the 6th is a y to the 3rd. And now underneath my radical, I still have a 2 and an x. For number 10, the largest perfect square here for 32 is going to be a 16. So it's 16 times 2. x to the fourth is already a perfect square. Y to the second is already a perfect square. And z I can't change to make it a perfect square. So now the square root of 16 is a 4. The square root of x to the fourth is an x squared. The square root of y to the second is a y. And now underneath my radical, I still have a 2 and a z. And that's it. Number 11, there's not much I can do here. I don't need to break up the 49 because it is a perfect square. X and y I can't break into perfect squares, so I'm just going to go right to taking the square root. The square root of 49 is a 7. And then the x and the y are still trapped. For this one, 81 is already a perfect square. X squared is already a perfect square. Z to the 11th I can break into z to the 10th times z. The square root of 81 is a 9. The square root of x squared is an x. The square root of z to the 10th is going to give us a z to the 5th. And now underneath my radical, I still have a z. These next couple are all cube roots, so they're a little bit trickier. But with a cube root, we're looking for perfect cubes. For this first one, the 54, I can break into 27 times 2. And now for perfect cubes with variables, I just look for exponents that are divisible by 3. So with this one, it's going to be an x to the third times x to the second. For y to the 8th, I can break it into y to the 6th times y to the 2nd. Again, we need exponents that are divisible by 3 because just like in my rules of exponents, everything's always one step back. So when I take a root, I divide the exponents, which is why they have to be divisible by 3. I take the square root of 27, it gives me a 3. And now here, the square root of x to the third, I divide the exponents. 3 divided by 3 is a 1, so it's an x to the first. The square root of, the cube root of y to the 6th is going to give me a y to the second. Again, it's division. 6 divided by 3 is 2. And now underneath my cube root, and make sure you still write it as a cube root, I've got the 2, the x squared, and the y squared. And that's it. For the next one, 24 I can break into 8 times 3. X to the third is already a perfect cube. And then y to the 11th I can write as y to the 9th times y to the second. And now I take the cube root. The cube root of 8 gives me a 2. The cube root of x to the third, again, I divide the exponents. It's x to the first. The cube root of y to the 9th, I divide the exponents. It's a y to the third. It's an ugly looking 3. Let me try again. And now I still need the cube root symbol, and I'm left with a 3 and a y squared underneath there. For the last one, the 250, I can break down the perfect cube as 125 times 2. X to the 7th, I can break into x to the 6th times x. And then the y, I can't really do anything with. I can't rewrite in terms of perfect cubes, so I leave it the way it is. Now I take the cube root. The cube root of 125 is a 5. The cube root of x to the 6th, again, I divide the exponents. It's an x to the second. And now underneath my cube root, I'm left with a 2, an x, and a y. Okay?